Welcome to the third and final workshop for Chipalooza. This workshop is on physical verification. And like I've done for the last few workshops, I'll give you a little rundown of the timeline so far. We've gotten through everything except for this workshop and layout being due. It is April 1st, and I was thinking about putting in a slide here saying layout is due tomorrow as a April Fool's joke. And then I thought, well, when I bring up the actual layout due and it says April 15th, that's not a whole lot better. Still seems like a joke. But it is April 15th is when layout is due. And the reason, as I have mentioned before, is that we have a Chip Ignite shuttle run that closes on April 24th. And we are trying to get as many of these layouts into that run as we can. So the goals of this workshop, the first part of this workshop is a holdover from the previous workshop, which I didn't get to go through all my slides. So we'll start with basic extraction for LVS, how to do parasitic extraction, including capacitance and full RC extraction. I'll say a little bit about layout best practices, and then go through a few specific requirements for the Chipalooza challenge. And then go into the main parts of physical verification, which is DRC and LVS. So with that, I'm going to do what I've done in previous webinars and set up my slides here where I can also look at where I can also have my browser in the background and some terminals to work in. So starting with basic extraction of layout for LVS. A lot of these things are what I would call recipes. There are a number of commands that you need to issue to Magic. The Magic's way of doing extraction is a two-step process. It wants to do first a hierarchical extraction in which it extracts things into these .ext files, and then from there it will combine those into the final SPICE netlist. So it is generally a matter of these four commands. I like to use, this isn't necessary, but I like to use extract path ext files that just puts all the .ext files into a subdirectory called ext files, where they don't clutter up your working directory. The main extraction is done with extract all, and then that's the first step. And then the second step, you want to set a whole bunch of options. There is this convenient function called ext-to-spice LVS, and that sets up all the options that you're going to need for both for doing LVS and for working with the Skywater PDK. And then finally, the actual conversion of the .ext files to a SPICE netlist is the ext-to-spice command itself, and the -p ext files is necessary because of I put these things in this subdirectory. For the most part, that's all that you need to know about extraction. It should be pretty simple. However, if you are trying to extract from Magic from a layout that you have created elsewhere, such as Klayout, then it's helpful to remember a few things. If you have created your devices in Klayout using PyMacros, you probably won't have this problem, but just to note, Magic has all these derived layers. I described that in the last workshop, and what it does not like is it does not like to have devices with all the layers that are needed to identify that device uniquely spread across different cells. So if you attempt to make an infet by having, say, your indiff in the parent cell and your poly in a child cell, that is not a device as far as Magic is concerned, and it will give you an error when you try to extract. It will say can't overlap those layers. So be a little cognizant of the errors that it gives you when it is extracting. It will give some other minor errors, like, well, not errors, but it'll give some messages that may look like errors where it says source and drain are connected. So if you have source drain tied devices, then you'll get messages in the output. Those are ignorable. If it says can't overlap those layers, then you probably want to see what's going on. Extraction with parasitic capacitance is pretty much the same script, because the original extraction, in fact, does all the extraction with capacitance. It's the X to spice, that second stage, that determines whether it's going to put those capacitors in the output or not. So the only difference between this recipe and the one before is I've added this line C thresh, which is the cutoff point in femtofarads of the capacitors that it is going to write to the output. I have also added this suggestion to set sub. This is the global node for substrate to 0, which is the global substrate node in ngSpice. And the reason is that you can generate parasitic capacitances to substrate when substrate isn't actually a pin of your subcircuit, such as if you have all your subcircuit in deep in well, you may have capacitive coupling all the way around it to the substrate. And this makes sure that ngSpice would actually know what that node is being connected to, because it's its global substrate. So just really quickly, here is my example layout, the instrumentation amplifier. So just a quick look at this. If I do extract path text files, extract all X to spice LVS and X, didn't like that, X to spice LVS, X to spice. Oop. Try that again. Extract X to spice LVS, X to spice. Ah, I forgot the -p X files. That's what happens when you use the path. And I go back and look at what is in my spice file. And this is the basic extraction for LVS. So all I have in here is devices. Now, if I want to get the parasitic capacitances, since it's only in the second step, I don't need to redo the second step. I can say X to spice C thresh 0.1 and then do my X to spice again. And this time, if I look at it, now you'll see that for each subcell, I have a number of parasitic capacitances in the net list. And so that's how I do the basic, just capacitance parasitics extracted. Now, moving on, how to do full parasitic extraction, which is the one that you really need to do especially for a sensitive analog design. Do not use X to spice R thresh. If you look up the command reference for X to spice, you will see R thresh. It looks like it is equivalent to C thresh. It is a form of parasitic resistance, but it's something called lumped resistance, and it only shows up in .sim files, and it is not read or understood by any tool that I know of. It's an interesting concept, but it's not the one that you want here. And what you do want is, in fact, a fairly large and complicated recipe that does full extraction. There are a number of steps involved, so I'll go through each one of them. The first thing to do is make sure that you flatten the cell, because full RC extraction is very hard to do in hierarchy, and I'm not sure it will even work in Magic. Once you have created the flattened cell, you want to load it, and then you can do the full extraction as usual. After that, you have to run X to sim, the only purpose of which is to create a file that saves all of the nodes in the layout. This is the main part that does the resistance extraction, which is X-resist. It has one option, which is to set the tolerance. This is not a cutoff in any value of resistance, because Magic doesn't want to say if you have a long chain of very small resistors, it could add up to a very significant resistance. So it's not going to cut off based on a resistor value. It's going to cut off based on a resistance value relative to the entire network. And 10 is it's a reasonable value. It's, I think, generally good for most purposes. If you think the output you're getting is too big or too small, you can play around with that number. The only way to really know what you're getting is just to try changing it and seeing how big the net list comes out to be. Once you have done that extResist, it creates a file that is used to annotate the original extraction, and then you just run xtoSpice more or less the same way as I said before. You set your defaults by using xtoSpice LVS, and then follow that with cthresh, so you'll get the parasitic capacitances, and then follow that with xtoSpice extResist on, so that it will annotate with the resistances, and then generate your output. Now, if you don't want to remember that recipe or write it out, you can save it in a script. There are other people who have created scripts for you. So one of those is, if you recall from, I think, the first of the workshops, I pointed to something called IIC-JKU. That's Johannes Kepler University. The two projects called OSIC Multitool and IIC OSIC Tools, the Docker container. So in OSIC Multitool, there are a bunch of scripts, and one of those is a script that automatically does the parasitic extraction. And given a -m option, it can do it in 3 different steps. So essentially, the recipes I already showed you, one slightly different than what I showed you. The first one is only caps to substrate. The second one is the first one I showed you with all the capacitive extraction, and then the third one is the capacitance plus resistance extraction. So this is likely the one that you want to use for getting your net list. It can also be done within case as well. I'll show that toward the end. So now a few comments about layout best practices. Let me bring up a couple of, well, I'll start with this layout.
Just 1 second, Tim, on the extraction. Yeah. Is that room temperature resistors for the net list, or is that a specific corner? And is that HRLC or LRHC? How does it determine the parasitic resistor corner?
That is a very good question, Andy, because I completely forgot about that aspect of it. So let me show that a second. So if I say, excuse me, bring that back to the front. If I say extract style, I am looking at the default style, and that is going to be extraction at typical. If I say extract style, give it some invalid thing, it tells me what are this styles that it knows about, and that includes the typical. It also includes these corner cases, which are HRHC, LRHC, HRLC, and LRLC. And those are the ones that you're going to want to use to test at resistance and capacitance corners. So it's going to be either high resistance, high capacitance, or low resistance, low capacitance, or either the other 2 corner cases. So yes, that is very useful to know.
Thank you.
You're welcome. So back to layout best practices. Best practice number 1, this is specific to Sky 130, but do not use local interconnect for routing. If you look at this one and I hide everything except for LI, you'll see that the LI I use mostly to create pretty solid ground and power planes. And here where there are devices, I am using almost no local interconnect at all. The only thing that I use local interconnect for is just to get myself from the device, poly or diffusion, up to metal 1, where I can do the routing. So if I add to that, the local interconnect and metal 1, you can see I have immediately gone up to metal 1. In fact, in the top, I'm doing most of my routing in metal 2. And that's because local interconnect is highly resistive. It is, if there's something that you would never want to route in poly, then you probably never want to route it in local interconnect either. Use dummy devices and symmetry for matching. I have not done that here. I mentioned briefly in the last webinar in which I was creating devices for Magic using these devices that I could just increase the count. For instance, if I wanted to make this resistor here have dummy devices, I could change it from, let's see, bring up the parameter list for that. I can change it from having repeat of 4 to repeat of 6, so then I'll have 2 resistors on either side to act as dummies. Make your power rails wide. Let me switch over to another one that I think is a better. This is a crystal oscillator design that I did. So right here, you can see the power rails. The power rails are covering the entire top and much of the bottom of it. So having wide power rails is the way to ensure that you don't have much IR drop. You have good power rails and you will have less problems when you do your RC extraction, and it turns your power supplies into resistive networks. Use plenty of contacts. You'll see here I have my contacts going like the entire width of the cell. Same thing is true for devices, particularly if you have like wide devices. Make sure that your source and drain are contacted to the full extent of the width of the device, because these are very high resistive contacts. These can be like 300 or 400 ohms per contact. So you want to have as many of them as you can, including for the usual reason of just it's better to have redundancy in your contacts because it makes the connections more reliable. Keep contact poly on both sides of the gate. I haven't done that here, but over on this side I have. It's particularly good if you have a really wide device to make sure that you have contacted it on both sides. It's also good for very short devices, because in this case I have room for only one contact. If I do CIFC cont, then I see there's only one contact on each side of the poly. So in order to get redundant contacts for this gate, I'll contact on both sides. And keep sensitive analog away from, sorry, I need to pop that up longer so you can see it. Keep sensitive analog away from digital signals. So that's why I was bringing up this layout, because this is a crystal oscillator, the analog part of it. The Pierce oscillator is over on this side, and then I've got a digital buffer on this side. And they are well separated by a gap, and the entire analog section is put in a deep in well to keep it noise isolated. But it's even more important if you have digital signals anywhere coming into it that are on unrelated clocks, things like that, then you do not want clock bleed through. So keep your sensitive analog away from digital. For specific challenge requirements, I have mentioned that all designs must be in deep in well, and the deep in well should be surrounded by a P substrate guard ring. I have, like this one, I have put in the deep in well, but I have not put the substrate guard ring around it. I do have a substrate guard ring close by in the digital section, but I should have another one completely surrounding the deep in well here. All gate inputs should be protected by diodes. In this one, I've got a connection that's going straight out to a pad, and I am putting a N diode and a P diode in here. This is acting like an extra ESD protection up at the beginning of the circuit. That's a general recommendation for ESD. In the other layout, which I had back here, I use diodes for a different reason, and these are inputs that are being routed internally. So this is the negative and positive inputs of my amp. And I'm connecting them to diodes just so that it will resolve antenna violations. That way it's much less likely that that routing this out to some other circuit is going to end up having that be an antenna violation. And I'm going to go through, when I get to the DRC section, I'll go briefly through antenna violations if you don't know what they are, what you're supposed to do about them. For an area requirement, I mentioned in the original webinar on Chipalooza that we were going to specify area requirements for the blocks, which we ended up deciding not to do. However, I would like to impose just a general area requirement to try to ensure that designs are done pretty compactly, and that is there is in case an area estimate. So if you put in a physical parameter for area, such as here for this amplifier, I have a physical parameter down here. If I have selected a netlist from layout, then it's an area check. It's to see what is the area of my layout. But if I have selected schematic capture, then it gives me an area estimate. So what it's doing is it's using Magic to create all of the devices that I specified in my schematic and saying, oh, what's the total area of all those devices? And it gives me a value. So if I run this check, it will tell me that the total area of all my devices is 2080 microns squared. And I managed to turn that into, this is the wrong one, an area of, if I type box here, it tells me that my area is 1940. So I actually beat the estimate by a little bit, mainly because I'm overlapping a lot of these cells at the guard rings. So that's why I say if you get the estimate for your device sizes, then you should be able to generate a layout that is somewhere between 1 and 2 times that estimate. If you're more than that, you're probably wasting space. Lastly, let's see, where did my other layout go? Pins, put pins on the boundary. So you'll see here that I've got pins. The input pins come out all the way to the edge of the cell on this side and all the way to the edge of the cell on this side. That makes sure that if you're putting this in, say, open lane and trying to get open lane to route the digital signals into your macros, that it will be able to reach all of those pins. Another constraint I didn't mention here is that don't put the pins too closely. If you are putting your pins at a distance that is the minimum metal spacing, then the router will have problems. So make sure that you're at least or twice that amount apart with your pins. But you know, these are analog blocks. They generally have few pins, so you can just space them out about as much as you want in most cases. In cases where you might have a digital bus of like 16 bits, that's where you want to make sure that you're not putting them as close together as possible, or you will cause the router problems. And I say put pins on higher metal layers. What I meant by that is that, for instance, if I have here the end of my resistor is in local interconnect, I am not going to bring this out to local interconnect for routing, at least metal 1. So remember that open lane is going to route in Sky 130 on metal 1, 2, 3. It's going to put power planes on metal 4 and 5. So, and these things are going to be put into a layout, and a lot of the digital may be routed with open lanes. So make sure that your pins are in a position so that it makes it easy for the router. The easier it is for the router with the metal 2s in the right direction for metal 2 routing, metal 1 in the right direction for metal 1 routing, the cleaner the result of the auto routing is going to be. Yeah, this is a slide left over that I never got to from the second workshop. I wanted to mention where I was talking about the parameterized devices in Magic. There is, in addition to all your standard devices like transistors, resistors, and capacitors, and so forth, there are another class of things in this menu that are essentially just helper scripts for drawing different things. So where I said I wanted the layout to be in a deep in well, it's easiest if you use one of these helper scripts. So I can make a box the size of my cell. I can go up here to devices 1 and select, where is it, deep in well region. And it will draw me the entire deep in well region with all of the design rules correct for the amount at which the in well has to overlap. So I highly recommend using that for your deep end well, because otherwise satisfying all these rules can be a real pain. So onward to physical verification. Design rule checks. When you look at any result of a design rule checker, you're going to want to understand what the rule is. So if you go to the Google Skywater PDK, that is here at github.com/Google/Skywater PDK. That's a good place to start, so you don't have to remember this, read the docs URL. But at the top of the Google Skywater PDK repo, there is a link here to read the docs. Click on that. It takes you to the documentation for Sky 130. From there, click on Design Rules. From Design Rules, click on Periphery Rules. And here you will see all these layers. So all the rules for each of these layers is just a matter of clicking on. So I want to see poly. I click on poly. And there I get all the rules related to poly. So in any DRC output, it's going to cite these rules. So you'll see it saying something like well, let me just create a design rule violation here. So I can put, let's say like metal 1, and I'm going to put another metal 1 too close. There's my error. If I say DRC-Y and move that other console out of the way, it says metal 1 greater than 3 micron spacing to unrelated metal 1 is less than 0.28, and it's citing this rule metal 1.3b. So I can go back to here, I can find metal 1 and metal 1.3b, minimum spacing of huge metal 1 to metal blah, blah, blah. So this is how you can reference the rules, and these rules come with illustrations that are somewhat hard to read, but basically illustrate all of the rules in the block above them. So I just showed you running interactive DRC and Magic. However, one thing I should mention is that there are different styles for DRC, and one of them is called DRC Fast, and one of them is called DRC Full. DRC Fast is the default. The reason it's default is because if you bring up a full chip layout and it starts doing a full DRC, it can slow down Magic quite a lot. So the DRC Fast is something that runs pretty quickly and satisfies most of the design rules for standard cell layouts. But you're doing analog designs, you want to use DRC Full. And that will catch a lot of extra errors that aren't included in the fast. And it's not going to, if you're just doing a small analog layout, it's not going to slow down Magic very much to do DRC Full. It just doesn't take that long to do all of the rules for a small analog block. You can also, if you're not typing that in, you can also go up to the menu. There's a DRC menu, and you can select DRC Complete. That will do all of the rules. Yeah, so let me show you with this, not this layout, but the other one. Not that layout, but where's the other one? It's back here somewhere. There it is. No, it's not that one. No, it must have been this one. Oh, it is this one. Okay, I can go to DRC Complete, and that just changed the rules. It didn't do any extra calculations, so I want to go to DRC and type DRC Update. And when I do that, I notice, oh, I got a rule error popped up. There's the error. I can see what it is. I showed you before how you can type the question mark or go to DRC, what is it, DRC report, or type DRC-Y on the command line. There's another thing that you can do, which is the DRC manager. I can go over to DRC and say, no, options, DRC manager. And I get a little window that tells me what my DRC errors are. So right now there is only a DRC count of 2. That is 2 error rectangles that are related to a single error type or a single problem. And I can go through here, and if I have a lot of errors and just want to find what the errors are, I can click on zoom and it will zoom in on that error for me. And if I want a report of all that, I can hit save and it will write me a report called drc.out that has all the same information, except all these numbers will be in microns in the file. I just skipped over this page. There's also, you can turn DRC on and off via this little DRC icon at the top of the layout window, and it also gives you the total number of errors. One thing to remember about, or to note about DRC errors is that sometimes you'll make a new parameterized cell and it will come up, and the parameterized cell will have errors. And you might think, well, why, if it's auto-generated, shouldn't it be error-free? Well, in this case, there are a few errors. This one is a minimum metal area error. So the generated cell is trying to bring up the connection to poly all the way up to metal 1, but it has absolutely no idea what your intentions are, whether you want to route out to the left or upward or to the right. And so it just puts the minimum amount of metal, and that's not satisfying the area rule, particularly if you have a minimum length device here. And so you get an error. But if you just draw over that with more metal, it's expecting that this has to be routed out somewhere. So you're going to route out with metal 1, and as soon as you've put enough metal connected to that pin, then the minimum metal area is satisfied and the error goes away.
Very quick tactical question on placement of an NMOS device inside deep NWell. The question was, do I need to place a P-well in deep NWell before placing an NMOS device?
Good question. The answer is no. And it's a good question because it really depends on the foundry as to how they define deep NWell in their process. So if I go in here and I do, where was it? Deep NWell region, everything inside, this is the NWell ring. The NWell ring forms like a wall around the deep NWell layer, which is buried. And everything inside of this is a P region. So if I want N devices in here, I just draw them in here. So I can just create a NMOS and put it in here, and that's fine. That is an NMOS inside a P region, which is inside my deep NWell. If I want to put a P device, then that's fine too. It's just going to have an NWell, and that NWell now extends all the way down to the deep NWell layer under it. So that's the thing to remember, is that if you are outside of a deep NWell, then any N device that you draw that is on the P substrate, they're all connected together because all of the P substrate is connected together. The opposite is true inside a deep NWell. All of your P devices that are in NWell are all merged together by connecting to the deep NWell underneath. So that's an important thing to remember. I briefly mentioned antenna errors and said I was going to describe them. So this is what an antenna error is. An antenna violation is something that is caused at manufacturing time. So if you have, for instance, let's say you have a net here, and the net is on metal 1, and it connects somewhere else in the chip on metal 2. At the time of manufacture, after metal 1 has been put down, but before metal 2 has been put down, this metal 1 just looks like this big, long wire hanging with the end not connected to anything. And it's an antenna, which means that during the manufacturing process, it can collect charge. And if it's connected to a very small gate and it's a very long metal wire, it can connect quite a lot of voltage. It can collect enough voltage that it will blow out this transistor gate. And that's why there are antenna rules which say that you must have a certain amount of diffusion connected to a line, or a minimum amount of metal, or maximum amount of metal that you're allowed to have to keep the gate from blowing. The way to solve these is usually to break up your metal line or to put a diode. That's why I was mentioning putting diodes on inputs to prevent there from being antenna violations when the router routes to the input of that cell. But DRC, these are DRC rules as far as the foundry is concerned. They'll show up in the DRC rule deck. As far as Magic is concerned, they aren't calculated like the rest of the DRC rules, so they are done separately. So there is a rule called antenna check that will do these kinds of antenna rule checking, and the way to run it is to say antenna check debug. That'll give you printed output that's useful for seeing what the errors are, and that will run the check. So I've prepared a little example here. So this is a minimum size transistor, so very small gate, and I've connected this giant wire to it. So that is definitely a antenna violation. So I'm going to say antenna check debug, and then I'm going to run antenna check. And immediately I get, you see these white stripes that appeared on it. So that's the feedback error marker. And because I said debug, I get all the information I need about that antenna violation, which is, here's the cell whose gate is going to get blown by that antenna. The antenna violation is detected at plane metal 2, which means my problem exists here on metal 2. The effective antenna ratio is 970, where the limit is 400. So I've got a wire that's somewhat more than twice as long as would be needed to blow out that transistor. And then it tells me where is the gate wrecked and where is the antenna wrecked, so I can track down where those are and fix it. And that's how antenna violations are detected. And just remember that having a DRC clean design means that you also need to have antenna rules checked and clean. Density is something I'm going to cover rather quickly. Normally, you don't need to worry about density, but density rules are part of the rule deck. And as far as analog designs are concerned, sometimes you do want to care about how fill generation is done over your cell, because fill generation can mess up your results for your cell. Sometimes people want to put the density fill patterns into their cell beforehand, or just to do that to see what is the effect of the fill on your circuit. If you want to do that, you can check the density rules. I'll say a little bit about actually doing the fill generation later, but just to check what the density is, it's also a different command. It's not covered by the normal DRC rules in Magic. There is another manufacturing rule deck, which we've made for Klayout. By manufacturing rules, I mean these are a set of rules that were given to us by Skywater. They represent rules that Skywater will not waive. They consider them to be manufacturing issues that can cause wafer-wide or trip-wide problems, or problems with parts of the mask flaking off, stuff like that. And so it is necessary for every circuit that goes to Skywater that it absolutely passes the manufacturing rule deck. It catches a number of rules that Magic doesn't implement, because Magic likes to do its own generated layers. So if you've got a layout that you created in another tool like Klayout, then you definitely need to run it through this deck. And for running DRC in batch, there are also scripts that come from the IIC OSIC tools or OSIC multi-tool, and they will run either Magic or Klayout scripts for you. So they're very useful to use. If you run it without options, just IIC drc.shell and pass it a cell name, you'll get a DRC output. It looks very much like the DRC manager that I showed you in Magic. It does have this little message at the end. This is something that's picked up from the implementation that we have in PreCheck for ChipIgnite, but it says the answer should be divided by 3 or 4. What that means is that Magic counts by rectangles. There will often be, say, 2 or 4 rectangles drawn for each actual error. And so if you want to know the number of problems that you need to solve, then you need to take the DRC count, which is a count of rectangles, and divide it by 3 or 4. So that's all that means. The difference between running the Magic DRC deck and the Klayout deck is just a matter of passing it the -K option, and it will run the Klayout rule deck. Right now, there's only the Magic full DRC deck and the Klayout manufacturing rule deck. So I don't think there's a option here for selecting the deck, because it's either the manufacturing rule deck in Klayout or it's the full rule deck in Magic. You can also run DRC in case by having a physical parameter that says DRC errors and is running this tool called case DRC, which is a Python script. Except it doesn't give you any detailed information at the moment. It just gives you an error count. So enough for DRC for now. On to LVS. For LVS, I recommend the tool Netgen. Netgen is a netlist conversion and comparison tool. It can compare two SPICE netlists, and a neat thing that it does is it can compare any combination of both SPICE netlists and structural Verilog netlists. And by structural Verilog, I mean Verilog that has been synthesized. So it has been turned from RTL, register transfer language, into actual instances of standard cells. So it's really just a netlist. It has cells and their connections. And so it can be compared just like any SPICE file. The reason I recommend Netgen is it has all these nice features. It does hierarchical comparison from bottom up. It'll start with the lowest level cells in your design and compare the lowest level cells and then the next level up and so on until it gets to the top. At each level of the hierarchy and at the top, it can do pin matching. It can do property matching, so it'll check the properties like width and length of devices. It will create and analyze series and parallel devices, networks of devices. So if you have a resistor, one long resistor in your schematic, but you've broken that up into a series of 10 resistors in your layout, it can figure that out. And it can do black box handling, which you need to be a little careful with because black boxing a cell is one way to just ignore possible errors inside it, but it's also a way of optimizing the comparison and making it fast for doing large jobs. I don't recommend that for small analog blocks. So if you want to get Netgen as a standalone application, clone it from my repository on GitHub. So under GitHub, rtimothyedwards/netgen, clone that, and it's got a fairly standard Linux type compile with the .configure, make, and sudo make install. But if you are using the Docker solution with IIC-OSIC tools, it's already there, and it is cloned and compiled in the same way here for OSIC multitool. And documentation can be found on my website, opencircuitdesign.com. Go to opencircuitdesign.com and go to Netgen. And there's not a whole lot there. The main thing that you want is the reference, which gives you the command line reference and a syntax reference for the setup file and for running LVS. Generally speaking, the one thing that you want to do with Netgen is just to run a simple LVS. And usually you run it from the command line, just give it netgen, and -batch means I want to run something in batch on the interpreter and exit afterwards. Then you give it a command. LVS is a scripted command in Magic. One thing that a lot of people don't realize or forget or never learn is that when you give two netlists to Netgen, SPICE netlists, they can be a library of subcircuits or they can be a test bench or something else. The best thing to do for Netgen is to give it a single file that contains a single subcircuit and maybe additional subcircuits further down in the hierarchy. But to Netgen, it's just going to look like a library of subcircuits. So you want to give its arguments in pairs. The first one is the name of the file, and the second one is the name of the cell you want to compare. And usually that will be the top level subcircuit, but you can also compare any two subcircuits in that file. And of course, it's LVS, layout versus schematic. So it's usually in that order. You want to give the layout netlist first, the schematic netlist second. Stick with that to keep from confusing yourself. The third argument is the setup file. So the PDK has a specific setup file for Netgen, which tells it what are the devices in the process and which ones are FETs, which ones are resistors, which pins can be permuted end to end. And then finally, the last argument is the output file. You can run Netgen with a GUI. If you run Netgen or Netgen-no console, you will get either this console window or it will just dump you into the Tickle interpreter, in which you can just give the LVS command. Not particularly any need to use this. Normally, you just run from the command line. If you want to do something more complicated than just a single cell in a single file, then it is often necessary to set up a script. The way to do this is instead of giving it the LVS command, you give it the Tickle source command. So you say netgen-bash source and then give it the name of a script. And in that script, you can do all sorts of things. So the purpose of this script is just to read in an extra file that doesn't exist in one of the net lists. So if you look through this example script I made, the first 3 lines are just setting up the pointer to the setup file from the PDK root environment variable. Then I read in the first net list by using the readnet spice command. That returns me a file number, so I set that to a variable name. Then the second net list, I do the same thing, set that to a different variable name. Then I want to read an extra file that isn't in either one of these. And so I will use the readnet spice, and then I will attach it to one of these circuits. And after that, I can just run the LVS command on the 2 variable names, circuit 1 and circuit 2. There's an example of that that's in the Sky130EF IP RDAC in my GitHub account, R. Timothy Edwards, that has an example under case. There's a script called run project lvs.tickle that's set up exactly this way so that it can read in the standard cell library for to pick up the high voltage standard cells because one of them is being used in the schematic netlist. And as you might expect, there is a nice simple script for this as well in IIC-OSIC tools, and that is called IIC-LVS.shell. Unfortunately, it only covers the simple case, so as long as you just have a single netlist with a sub-circuit in it, and if your sub-circuit has the same name in the layout as it does in the schematic, then you can use this script with -s for the schematic name, layout name, and cell name. And it has the additional function that you can give it a schematic or a GDS or .mag file, and it will automatically extract and do schematic capture and give you the netlist. Interpreting Netgen output is always a fun thing. It's a learning curve. Just from a very high level, the output of Netgen looks like this. You've got a comparison with your layout on the left and your schematic on the right, if you have given it as layout first, schematic second. And for each subcell, you will get a circuit summary. It will tell you what are the devices in that cell and how many devices are in the layout, how many devices are in the schematic. If everything matches, then you're all good. But the problem is when things don't match up, then you will get a mismatch, and that will be followed by a dump of nets that it thinks are not matching. One of the most common cases is you have a short or an open, in which case you will have more nets on one side than the other. So in this example here, I've got 2 nets, power and ground, that are in my schematic, but in my layout, I'm seeing 4 different nets. And if I look at each net, it is followed by a list of all the number of each kind of device that is connected to that net. So what this output is telling me is that there are 3 devices, total 2 and 1, that are connected to the ground net. One of them has a source or drain. That's this 1 or 3. So it's permutable. It doesn't care which end is which, source or drain. So it's saying there is a device, either its source or its drain is connected to ground. And then there are 2 devices here. Pin number 4 on a FET is the bulk terminal. So it's saying it's got 2 NFETs whose bulk terminal is tied to ground. Over here, those are split into 2. So I've got my V ground net is connected to a NFET source or drain, but the bulk terminal here for 2 NFETs is connected to some other net. So that tells me immediately that over in my layout, I have got a floating well and substrate that have not been tied to my power and ground. Now, this is an actual example, and this is also a good example of hierarchical matching, because this actually exists in one of the I/O cells. So in the Skywater I/O cell netlist, there is a NAND2 gate, and it is actually drawn like this. The schematic does not match the layout, and the schematic has the well and substrates connected to the power rails, and the layout doesn't. And Netgen will note that. It will note that they do not match. And at the end of it, you'll see it says flattening non-matched subcircuits. So it decides, oh, maybe it's just an issue at this level of hierarchy. So I'm just going to flatten those and see if it resolves itself at the next layer of hierarchy up. And in the case of the I/O cells, yes, that's exactly what happens. You go up 1 or 2 levels of hierarchy and it all works out. And at the end, it will match. But it's always good to make sure that your schematic and layout match as much as possible so that you don't end up with weird errors like this where you stare at it and you don't know why it happens. And it's only because you didn't bother to make your layout and your schematic look the same. In the best case, you will get a circuit summary. It says, here's the layout netlist, here's the schematic netlist, all the device counts match up, all the devices and all the nets match up, and it says circuits match uniquely. If you're used to running Calibre, that's the equivalent of the little smiley face. And that's where you want to get to. In some cases, it's a little more complicated. What you'll see is it says that it has read in one circuit, and then it says the circuit was modified by parallel series device merging. So it tries to match things exactly as it sees them. And if it can't do that, then it runs through a phase where it tries to see, oh, if I combine some things in parallel or series, let me see if I can get the 2 sides to match up. And if it can do that, then it will run again. And in the best case, that can also be LVS clean, and you'll get a circuits match uniquely output from that. If there are property errors, it will do a property match check. And if there are property issues that are different between the 2 sides, and instead of saying circuits match uniquely, assuming that it's topologically correct, it will say circuits match correctly, and then it will be followed by a block that says there were property errors. And after that, it will give you your left side versus your right side, and you'll have to look through the list of properties that it dumps and say, okay, how is it different on the left side, and did I swap 2 things that were supposed to be the other way around? I've already showed you this. If you want to run case for the final sign-off values of all the parameters, you want to go over to the top, and where it says netlist from, there's a drop-down menu. The final sign-off should be done with an RC extracted netlist. So all you need to do is make sure that's on RC extracted, and then run all of your simulations in case to get your final answer for the spec, the performance versus the spec. An important thing to remember is that when you're doing that, what it's doing is it's swapping in a netlist. So it's taking out the schematic netlist and it's replacing it with the RC extracted netlist. It can only do that if your netlist is separate from your test bench. And so it's important to set up your test bench to use this .include path, dot meaning device under test. And if you do that, case is going to take the symbol that you use. It's going to treat that as a black box. It is going to match that up with a file that is the netlist that it includes from the place where case dumps its netlist. So when you change this to RC extracted, it is going to dump the netlist into netlist /RCX / name of cell dot spice. And that's what will get included here. Since I have we're sort of running out of time, I want to give a little time for questions and answers. So I'll go through this really quickly, and then I'll leave this in the slides that I post to the Slack channel later. But for doing fill pattern generation, there is something called CIF-O style, which is the style that it writes GDS in. Normally, you leave this alone. If you're just writing GDS, you don't touch this at all. But if you change it to CIF-O style waffle fill, then you can use this command sif paint, and this will allow you to run the rules from the fill pattern generator in Magic to create an output. So I can show that. Let me just show that really quickly because it's a little complicated. So if I like make this big, let's just make something in, not that, in metal 1 and make a big space in the center. And then I do, what is it? Sif O style waffle fill. Sif O style waffle fill. And sif paint, I want to give it the like metal 1 fill and metal 1. Metal 1 fill, metal 1. And it didn't like that because it is not metal 1 fill. I have written that wrong on the page. It is met 1 fill. And I drew a little bit outside the boundary there, but you can see that is the fill pattern that is, and it's been represented here in metal 1 blocks. And so if you want to pre-fill your layout just to see how that extracts and affects your performance, then that's how you would do it. You can also prevent fill by putting a fill block layer over your cell. I don't recommend doing that unless you have to, because too much, you're making the area effectively unfillable. And if any design has too much unfillable area, then it will not pass density rules and it will get rejected by Skywater. So be very careful. Don't do this on any large area, but it's fine for just small sensitive areas of your analog where you don't want fill messing with your circuit. So to wrap up, we have some deliverables for the layout phase of the Chipalooza challenge. The main one is that you get us layout in GDS format. If you have done your design in Magic, then we want to see all of the .mag files that are part of that design. And we want simulation results. Don't forget, simulation results must be across corners, and it must be using the RC extracted layout, just as I've shown you. If by doing it across corners at an RC extracted layout, you are not quite meeting spec, then I suggest you should just get the layout in on time and worry about revisions afterward. If you're not meeting the spec by a lot, then you should worry about fixing your layout to improve it. And of course, we want to see that the final design is DRC and LVS clean. And I want to reiterate that DRC includes both the DRC decks and antenna rule checks. And make sure you have pushed all of your design files back to your repository by or on the end of day, April 15th. A little preliminary information on the post-layout design review. I think the design reviews were scheduled from April 17th. And I will do it in the same way that I did the design reviews for schematic and simulation, which is I will post a calendar, and it's a system called Calendly, and you can sign up for a slot. We will do our best to give you more time for this design review. I will try to allow an hour at least for the post-layout design reviews. So thank you very much for attending this workshop. And if you've attended all the workshops.
We got about 10 questions, Tim, we should try to run through before we drop.
Yeah, no, I was planning to say right now I'm ready for some questions and answers. We're at the top of the hour, but we'll see how many we can answer in the next 5 or 10 minutes.
Is there a limit for how large a loci rectangle can be? It's from Louis Rodolfo.
Sorry, a limit for?
A locali rectangle can be.
Oh, a local eye rectangle. The local eye rules are written very strangely. What they limit is the aspect ratio. So there is no particular size limit, but they don't want it to have an aspect ratio of more than 10:1. And that is not even able to be checked in Calibre, as far as I know. So it's really just a recommendation. They also recommend that LI always be strapped up to metal 1. So honestly, if you've got the RC extraction will tell you just how resistive you've made a network. And if you have tried to route something in LI, it is going to show up in your RC extracted net list. So, use your judgment on that.
Next one is it possible to do R plus C and R plus C plus coupling capacitors with a magic extraction? And I knew how to do the last one, that's option 3. Question is, can you do R plus C only as part of the magic extraction flow with your options today?
Yes, you can. There is, so to separate, I didn't mention this in the talk, but to separate the coupling capacitance from the substrate capacitance, it's done in the extract command. So you need to look that up in the extract command reference in Magic. I believe it's extract no coupling, maybe. Look it up, but it is, you can separate all 3 of those, yes.
Okay. Next up is fill generated, how to see it in final GDS. I think we went through that live. And next
yes, although I should say, once you've generated fill, and probably the best way to see it is just to look at it in Klayout.
Yeah. Okay, next one is how to use the wiring tool in Magic and draw interconnect of a specific width. It usually starts with a default width. Can I control the width before starting to route?
Yes, you can. What I usually do for that is I will create a box and make sure the box is the size that I want it. So let's say I wanted a 1 micron wide metal one. I'll just say box width 1 micron, and then paint that layer just to start up. So that's my starting wire, and then I can go to the wiring tool and start from there. Okay, and that's how I get a specific size.
Anonymous attendee asked, can we please add the smiley face? It's very encouraging for people when LVS is clean. And I said, request submitted.
Yeah, I know, but I need to know first, is that smiley face trademarked by Mentor Graphics, now Siemens? That's been my worry.
We can add a different smiley face. That's not a problem.
Is the concept of a smiley face
absolutely not.
Okay.
Absolutely not.
All right.
Okay. A list of all of the checks before you run tape out. So a complete list of physical verification checks. Does that exist?
Yeah, maybe not. I will write one up and make sure I post it to the Chipalooza Slack channel. But it's probably something that we should have somewhere generally available to everybody.
Yep. Anonymous attendee, sorry, no, Brady X asked, after extraction and modifications need to be made to schematic and layout, is there a quick way to update the layout from Magic with changes coming from schematics? Or do you have to do that manually?
No, it's actually, I have a reentrant version of this, what is it, the file import spice. So if you have a layout and you import spice from an updated schematic, it should be able to find the things that changed, and it should modify just those things. Don't trust it implicitly, so make a copy of your layout just in case. But
I don't trust that the layout is clean after those modifications were made either. Yep. Oh,
the layout is definitely not going to be clean, and it's going to change those devices probably by placing them off to the side and in random places. So it will need a bit fixing up afterward. But that at least saves you the trouble of trying to find the devices and making all the same changes in the layout as you did from the schematic manually.
And only 2 more questions. Saeed Ahmed asks, can we draw the layout of an RRAM device that's connected between 2 metal layers? Can we draw the layout of a resistive RAM device that's connected between 2 metal layers?
Yes. That I will consider not a Chipalooza specific question, because we are not doing ReRAM for Chipalooza. But and I'm not set up here on Sky 130B, but there is a ReRAM device, and it looks like a via, and it takes the position of a via. It's between metal 1 and metal 2. Okay. So in Magic, it looks just like a contact.
So two more questions, and I'm sorry for kind of rushing you along. Easy.
No problem.
Can we get some references for layout placement? So some instruction, and then Viet Dang's question is almost exactly the same. Are there good recommended app notes for how to do physical verification and layout design? Complicated question. Sounds simple.
Yeah, it is. I have done a number of videos on that, and some of them were with VSD, so they're not immediately available. If I could rework some of those into videos for eFabulous, that might be nice. I don't know off the top of my head where to find videos specifically related to physical verification.
So I consider both of those requested, and we will go figure out how to find something. I'm not sure if we'll be able to get it online before the end of this challenge, but both of those requested, and Tim and I will follow up on how to get more content.
Yes, agreed. It's definitely something we need.
Yep, got it.
If we can't find it, we definitely need to make it.
Exactly. That was it. That's all the questions we've got content for. Okay,
that's we'll call it a wrap then, and look forward to seeing all of your layouts on the 15th. So
thank you very much, everybody.
Thank you, and take care.